Good morning, everyone. Today we will discuss about conduction fundamentals. Heat conduction is basically diffusion of energy. Heat conduction is governed by Fourier's law. Fourier's law is phenomenological. It is derived from observed phenomena. Joseph Fourier, the famous mathematician, published his remarkable book in 1822. He formulated a complete exposition of the theory of heat conduction. Experience arising out of the physical observations suggested two guidelines about the flow of thermal energy, which often referred to as heat flow, that results from temperature non-uniformities in a body. We have already mentioned that Fourier's law is phenomenological. It is derived from observed phenomena. A cylindrical rod of known material is insulated on its lateral surface. We can see this from the picture, while the end faces are maintained at different temperatures. One end is electrically heated, maintained at a temperature T1. Other end is cooled and maintained at a temperature T2. T1 is greater than T2. Temperature difference causes conduction heat transfer in the positive x direction, and x direction is aligned with the axis of the cylinder. We are able to measure the heat transfer rate Qx, and we seek to determine how Qx depends on delta T, the temperature difference, delta X, the rod length, and A, the cross-sectional area. If we hold delta T, that means temperature difference, and delta X, length of the rod, constant, then we will see by varying A, Qx will increase. Qx varies as A. If we hold delta T and A constant, we will see Qx varies inversely as delta X. If we hold delta X and A constant, then we'll see that Qx varies proportional to delta T. Qx varies as delta T. So we can see Qx varies as A, Qx varies inversely as delta X, and Qx varies as delta T. The collective effect is then Qx varies as A multiplied by delta T divided by delta x. If we now change the material from metal to plastic or some such change, we shall find that the above proportionality remains valid. We shall also find that for equal values of A, delta x and delta t, the value of Qx would be smaller for plastic than metal. This suggests that the proportionality may be converted into equality by introducing a coefficient that is a measure of material behavior. And we can write Qx equal to Ka delta T by delta X, where K is the thermal conductivity of the material. So it defines thermal conductivity. Unit of thermal conductivity is watt per meter Kelvin. Evaluating this expression in the limit as delta x tends to 0, we obtain heat transfer rate. So we can get the expression Qx minus Ka dt by dx, dt dx. This is formally the governing equation for heat transfer rate, or heat flux, which is heat transfer rate per unit area. Qx double prime is equal to Qx by A equal to minus K dt dx. Negative sign is necessary because according to second law of thermodynamics, heat is transferred in the direction of decreasing temperature. Dt dx between 2 points, if we have to write T2 minus T1 divided by x2 minus x1. x2 minus x1 is the length. It's a positive quantity. T2 minus T1, since T2 is less than T1, it will be a negative quantity. But heat flux is a positive quantity. In order to take care of T2 minus T1 divided by length, this minus sign in equation 2 comes into play, which takes care of heat flux and also takes care of that the heat flux is in the direction of decreasing temperature. So this takes care of second law of thermodynamics. Equation 2 implies that the heat flux is a directional quantity. The direction of Qx double prime is normal to cross-section area A. More general is direction of heat flow will always be normal to a surface of constant temperature called isothermal surface. This figure shows the direction of heat flux Qx double prime in a one-dimensional coordinate system where the temperature gradient dt dx is negative. Again, from equation 2, it follows that Qx double prime is positive. The isothermal surfaces are the planes normal to x direction. Now we can write a more general statement of conduction rate equation as Q double prime equal to minus K grad of T minus K I del T del X plus J del T del Y plus K del T del C, where this del operator is basically a three-dimensional operator. It's also sometimes called nebula operator, and T is the scalar temperature field. It is implicit from equation 3 that the heat flux vector is in a direction perpendicular to the isothermal surface. An alternative form is therefore Qn double prime equal to minus K del T del N. N is the normal direction on the surface of interest. The heat flux vector can be resolved into components such that in Cartesian coordinate, the general expression for Q double prime is I Qx double prime plus J Qy double prime plus K Qz double prime. And then we can equate equation 3 with equation 5, and we will get heat flux in 3 different directions. Exactly that's what we have written from equation 3 and 5. Qx double prime is minus K dt dx, heat flux in x direction. Qy double prime is minus K dt dy, heat flux in y direction. Qz double prime equal to minus K del T del C, heat flux in z direction. It is also implicit in equation 3 that the medium in which the conduction occurs is isotropic, homogeneous and isotropic. The material is not a material which has any internal anisotropy. It is isotropic material. So the heat fluxes in 2D, we can see x direction heat flux and y direction heat flux. We get resultant heat flux Qn double prime. Now, what are the key features we get from Fourier's law? It is a generalization based on experimental evidence. It defines an important material property, which is thermal conductivity. Its unit is watt per meter Kelvin. It is a vector expression indicating that heat flux is normal to an isotherm. Heat flux in the direction of heat flux is always in the direction of decreasing temperature. Decreasing temperature means favorable temperature gradient. It applies to all matter regardless of its state. That means solid or fluid. Fluid can be any liquid or any gas. Therefore, we can write the expression for thermal conductivity from Fourier's law as K equal to Qx double prime divided by minus del T del X. For a prescribed temperature gradient, the conduction heat flux increases with increasing thermal conductivity. Quite obvious. In general, the thermal conductivity of a solid is larger than that of a liquid, which is larger than that of a gas. Here we have given in a tabular form the ranges of thermal conductivities of gases, liquids and solids in order to form some idea about the value of thermal conductivity. Like gases, for carbon dioxide it is 0.015 watt per meter Kelvin, whereas for hydrogen it is 0.175 watt per meter Kelvin. Liquids, oils, the thermal conductivity is in the range of 0.2 watt per meter Kelvin. For water, it is 0.6 watt per meter Kelvin. Of course, it's a function of temperature. It may be 0.65, it may be 0.55. The range is around 0.6. Mercury, liquid metals are having little higher thermal conductivity, 8.5 watt per meter Kelvin. Non-metals, typically plastics, are in the range of 0.36 watt per meter Kelvin. Oxides are in the range of 10 watt per meter Kelvin. Tens of watt per meter Kelvin, 60 watt per meter Kelvin, 50 to 60 watt per meter Kelvin. Pure metals, zinc, 100 watt per meter Kelvin. Usually, for pure metals, thermal conductivity is very high. Here we can see for silver, it is 450 watt per meter Kelvin. In general, thermal conductivity for a pure metal decreases with temperature, and alloying elements tend to reverse this trend. So the net effect is that thermal conductivity of a metal increases with increasing temperature. This can be represented over a wide range of temperature, and K is given by K naught 1 plus B theta plus C theta square, where theta is basically excess temperature over a reference temperature. T minus T reference is theta, and K naught is the conductivity at the reference temperature, T reference. So K equal to K naught plus 1 plus B theta plus C theta square. So it becomes a function of temperature, and theta is basically temperature over the reference temperature, excess temperature over the reference temperature. So as theta increases, K increases. Since the intermolecular spacing is much larger and the motion of molecules is more random for the fluid state than the solid state, the thermal conductivity of liquids and gases is therefore generally smaller than that of the solids. Thermal conductivity of liquids usually temperature dependent. Thermal conductivity of the liquids usually temperature dependent, but it is insensitive to pressure. Liquid are, usually the working liquids are water or, some alkalis, some, acidic solutions or some chemicals. But the water thermal conductivity, here we have written as 0.556 watt per meter Kelvin, which is, I mentioned it earlier, which is around 0.6 watt per meter Kelvin. It's a function of temperature, has the highest temperature conductivity of all liquids except the liquid metals. Thermal conductivity of most liquids decreases with increasing temperature. Thermal conductivity of a gas increases with increasing temperature, but is essentially independent of pressure for pressures close to atmosphere. So gases thermal conductivity, we usually what we encounter is that thermal conductivity increases with increasing temperature. And also to be mentioned that essentially it is independent of pressure for the pressures close to atmosphere. So we will stop here today, and in the next class we will study some more aspects or deeper aspects of conduction heat transfer. Thank you. Thank you for your interest.